Good morning, good afternoon, good evening, whenever and wherever you are. My name is Anna Rochelle, and today we are looking at Algebra 2, Chapter 5.6, Inverse of a Function. This is Big Ideas, California Common Core State Standards. We are going to talk first about some vocab slash important information in this chapter before we get started with, I think, 5 or 6 problems in this video. So brace yourself, buckle up, buttercup. This is inverse of a function. All right. So the very first thing that I notice most students tend to forget is that they forget that the f of x symbol is actually the same thing as y. So anytime you see f of x, anytime you see y, they're totally interchangeable. There is a difference, but it's for calculation purposes, there's not really any difference. Okay. So I want to make sure that we are well aware of that. That is number one. The second thing that I want to talk about is when we are looking for the inverse of a function, we want to understand that inverses come in pairs, right? So peanut butter and jelly, right? Macaroni and cheese, those are things that come in pairs. And we want to make sure that we understand that all of these functions that we're going to look at, those are pairs. They're coming together and they're related somehow. Okay. And the way that they're related is actually they reflect over this y equals x line. So if I were to get my handy dandy fancy pants not calculator, but maybe a graphing calculator or desmos, and I would graph, that is a terrible line. Holy guacamole. Okay, let's make this a little bit better, a little bit cleaner. Okay, so let's say I have, that's also a terrible line. Yikes. Okay, we're gonna make pretend like that works. And I have here like my x-axis, my y-axis, and going across in this direction, I have my y equals x line, okay? So when I have this line, this is my super important line, meaning whatever x equals, y equals the same thing, whatever y equals, x equals the same thing. And so let's say I have a function, I'm trying to think, let's see, let's say my function looks like this. I know that my graph that is going to be the opposite of this function is going to reflect in this manner. So my graph will likely go somewhat like this. Holy cow, these are terrible in comparison to what Desmos would do. I would strongly recommend maybe going into Desmos and typing in like y equals, x and then y equals 1/2 x. In fact, maybe let's see if I can do this. So maybe not like, so 1/2 x, let's say, is kind of like in this corner here, 1/2 x. I'm terrible at drawing things on the computer. And then we've got, so this is negative, but we want like a 2x version. So maybe 2x might go somewhere like this. Because I'm going up 2 over, oops, up 2 over 1. And so we're looking at this like opposite direction. So we're kind of looking at this from the perspective of a fully reflected line. The pink reflects over this y equals x line and becomes the blue, or the blue reflects over the other line. I also don't think that these particular graphs are the best, but I also don't want to get you too confused until we get further on. And then I would have Desmos handy open up in another tab while you're watching this video, so that you can actually graph those and see what happens. And I'll give you a reminder to which graph you want to go ahead and use that function for the Desmos piece. So the other thing that I want to talk about is tables of inverse functions. So when we look at tables of inverse functions, we're really looking at just ratio tables from like middle school. We either have ratio tables that look like this or ratio tables that look like this. Sometimes instead of y, they'll have f of x. Sometimes instead of Instead of that, they'll have f of -1 with like this -1 on the top, or sometimes it'll be like g of x. It'll look a little different. But for the most part, they're both the same. One of the things I do want you to notice when you're looking at inverse functions, let's say I have -2, -1, 0, 1, 2 down here for my original function. Let's put this 2 down here. And then I have, I don't know, 7, 8, 9, 10, and 11 as my ratio table for this particular function. When I look at my ratio table or my table of values for my inverse function, what I want to happen is my x and my y need to flip-flop, okay? So one of the things that I'm going to notice is that the x and y are going to flip-flop, and once they flip-flop, then I have my inverse. So if this is my original function, let's say this is my f of x, my g of x, my other function, all the y values are going to go plop into the x values, and all of the x values will plop into the y values. So I'm going to end up with -2, -1, 0, 1, 2. And that's how you know that those two functions are going to be inverses. So we really want to make sure that we have that bit covered. Whoops, didn't want to delete all of that. And the last thing I want to talk about is the vertical line test and horizontal line test. So we know that the inverses are kind of pairs of each other. We know that we're gonna replace the f of x with the y. We know that the inverses also reflect on this y equals x line. We know that the tables are gonna help us by we're gonna flip-flop the x and the y values however we can, however we must. And then we also remember that whenever we have a function, so for example, if I have a function that looks like this, right? I know that if I take my vertical line test, my y-axis, I know that my graph will never hit more than one point at a time vertically, right? However, my graph will hit multiple places horizontally. In fact, if I take a look at this, I'm going to have one here, one here, one here. Like I'm going to hit, my x-axis is going to hit this graph so many times. I know that this will not be an inverse function because this will technically need to be rotated, right? Or reflected on this y equals x line. So it'll rotate, it'll translate. And so this will not be a actual function. However, if we look, for example, at this x cubed function, oh, that's actually a pretty good graph. Look at me go. When I look at my vertical line test, my vertical line test is fully passed, right? And then my horizontal line test also fully passes, my function fully passes the horizontal line test, right? Meaning I know that my function is going to be a function as is. So the x cubed function is going to be a full function, and the inverse of x cubed is also going to be a function. Sometimes, as I said here, they will not be. So let's go ahead, let's take a look at some problems. We're going to talk about finding inverses. We're going to talk about how to graph them, and then we'll see what's happening on both cases. Okay, so we're going to start off simple and then get harder and harder and harder as we go through the video. So definitely pause when you need to, and also make sure that you have desmos open so that you can graph this and the inverse. And then I want you to pause it because I will not show you the graph in the video. Okay, so you're gonna have to kind of like tag team both. Okay, all right. So step one, when we are trying to find the inverse, we are going to flip-flop these x and y values. Just like we flip-flop the x and y values in the tables, we're going to do the same thing here in order to solve for the inverse. So now I'm going to have x equals -1/2 y plus 4. That's step one. Once we have step one down, step two is pretty simple. Well, actually, all the calculation happens in step two. So just kidding. It is not pretty simple. Although it might be. I don't know. I think it's a lot of fun. So here's what's going to happen. You are going to get y by itself. That is your goal. Your goal is to get y on its own. That's what you want. So in order to get y by itself, I'm going to first subtract 4. I'm going to inverse operations, right? I'm going to use inverse operations to solve this equation. I'm going to end up with x minus 4 equals negative 1/2 y. Then I want to eliminate this 1/2 or negative 1/2. So I'm going to multiply by negative 2 on both sides. This is kind of going to go in this parentheses. Now, some teachers will be totally fine with this. I feel like it is not algebraic, and I would recommend that you stay away from that. Actually, this is supposed to be a negative. So I would go in and I would just distribute fully and call it good. So this is my inverse, and this is my original graph. So if you do graph them, when you go in, you'll graph 1/2 x plus 4. So you'll probably start somewhere at 4. You'll go down 1 over 2, down 1 over 2, down 1 over 2, kind of in this direction. And then when you go for 8, you're going to be here, and then you're going to go down 2 over 1, down 2 over 1, down 2 over 1, and you're going to be kind of in this direction. So when you graph in Desmos your graph, you're going to have this y equals x line here. And you'll see that they really are reflections of each other. You'll see kind of like if you tilt your head a little bit, you'll see that they really do very nicely reflect over each other. Now, with the next problem, we do have some this piece of information that's kind of important. It's this x is less than or equal to 0. So I'm not quite sure if you have the ability to put in just this f of x, this function here, and just give Desmos parameters, but I want you to not look at the other piece, because when Desmos graphs this, it's going to go in and it's just going to stretch your typical x squared graph by a factor of 4. But they're saying they don't want anything less, they want everything to be less than 0. So this whole section of the graph will not be there. In fact, let's see if I can cancel this out with a white. There we go. Okay, so that's how your graph should look like, okay? Once you give specific parameters in Desmos. Again, I don't know if they will allow those parameters. And so we're gonna go back to find a function. So we're gonna first we're gonna actually replace this with y, and then we're gonna replace the y and the x. So we're gonna end up with x equals 4y squared. In order to get y by itself, I'm gonna divide both sides by 4. I'm going to end up with x divided by 4 is y squared. And then I'm going to square root both sides. So when I square root both sides, I can't really take the square root of x, so I'm just going to leave square root of x. And then I have this 4 right here. And so the square root of 4 is 2. So I'm going to leave that. And I'm going to have that equals y. Now, if we take a look at these points, we know we're going to have 0, 0. We'll likely have -1, +4. We'll have -2, +16. Oops, somewhere up here. And if I were to create a table of values just for those 3 points, right, 0, -1, -2, I would have 0, 4, and 16. Again, remember the x and y, they flip. Inverses flip, right? They're the same numbers, just backwards. Okay. So my function, this function right here, is going to have these particular points given these parameters. My inverse function, this one, is going to have, whoops, that was not correct. I wanted x and then y. Really mean. My inverse function is going to have these numbers in for x and these numbers in for y. So I'm going to go 0, 4, 16 on x and 0, -1, -2 for y. Again, definitely if you can go in and graph them, but you'll see that it'll look like this. And then in this case, I mean, this is a little bit more looped, this is a little bit more straight, but you get the idea. They kind of look like they're making this like curved line where my main xy x equals y line gives that reflection line. Okay, so take a minute, graph these two, take a look at what they look like so that you have a visual representation, because at some point you're not going to be allowed to see these like through with table, okay? All right, so sometimes we're being asked to like take a look at different funky things. So let's take a look at this one. So again, I'm still going to look for the inverse, and you're still going to graph these in desmos. So I'm going to replace this with y. I'm going to get this as is. Then I'm going to replace the x and the y. X goes in here. Y goes in here. And I want y by itself. So step one, get the radical on its own. We divide by 2 on both sides. X divided by 2 is the cube root of y minus 5. I need to eliminate this cube root, and the only way I know how is to cube it. So I'm going to cube both sides. I would not recommend leaving this like that. I would recommend going in and being like, okay, x to the third power over 8 equals y minus 5, and then add 5 to both sides. So y equals x to the third over 8 plus 5. Another way you could write this is y equals 1/3, 1/8 x to the third plus 5. I feel like this is a little bit more algebraic than this because this is not quite as slopey. But either or should work in desmos, okay? And so the instructions for this problem were find the inverse and graph it, okay? Same business for here. We're going to do the same thing. We're going to replace this guy with y, and then we're going to flip-flop these two. So I'm going to end up with x equals y to the fourth plus 2. Get y on its own, so we're going to subtract 2 on both sides. X minus 2 is y to the fourth. Now, I need to eliminate this y to the fourth somehow. And again, the only way that I know how is to fourth root it. So when I have the fourth root of 4, those guys pretty much cancel, and I'm left with just y. And then I have y is the fourth root of x minus 2. Some of these functions may look a little wonky and maybe not quite functiony enough. So for example, this x to the fourth generally looks like, that is not very nice. It's like a little bit wider on the bottom. Not quite so much like a U, it's more like that kind of business. And then when it's added by 2, we just move it up top. So I'm just going to move this guy down too, so that I don't have to redraw that graph. And so this is my original function. You'll notice that these are generally they don't have inverses, because if I were to reflect it, it would go kind of like this on my y equals x line. And this is not a function because it does not pass that vertical line test. So one of the ways that you would know that originally, before you even attempt to try to graph the other function, the inverse function, you would take a look like, oh, does it pass the vertical line test? Yes, it is a function. And then does it pass the horizontal line test? No, it doesn't. And so therefore the inverse is not a function. So one of the reasons why I'm encouraging you to use desmos so much more in this video than in any other video, I feel like it's because you need to visualize them, because eventually you're going to be asked to determine whether the functions are inverses. And so what you're going to need to know is certain functions can be inverses and others cannot ever. So for example, I know that this can actually be rewritten as 1/4. That is like a weird looking form. 1/4 x minus 3/4. So somewhere along the line, I'm going to find negative 3/4, and I'm going to go up 1/4, and I'm going to go in this direction, right? That's kind of what this graph is going to look like. This graph is going to say, hey, I'm going to find 3, and then I'm going to go up 4 over 1, or down 4 over 1, and then I'm going to go kind of like this. If you take a look, these will be in desmos. These will be inverses of each other. These will look like they are inverses of each other. Actually, I don't know if they are exactly, but they will look it, right? And they will at least be functions. Some of them will not be functions. Okay, so I want that to be very well stated. Every single time you solve a problem in this particular unit, I would graph both the original function and the inverse, just so that you can visualize it. Okay. All right. So thank you for coming to my TED Talk. Moving on. 2 ways that you can solve this type of problem by when they ask you determine whether or not the functions are inverses of each other. So option 1 is you can graph them and see if they're reflections. Option 2 is you can choose a set of points and create a table of values, X and Y both, right? And then do the same thing, do those values work for this one, but flipped, right? Option 3 is you take this one and you make an inverse, and does it turn into this function? Or you take this one and you put it into that one. So there's multiple ways. My favorite way is to actually go in and solve one of the problems. Since I've done that way up until now, I think I'm going to let you guys do it that way on your own. I am going to show you a different way. So the other way is to actually take my g function and place it into my x, and then solve this. So for example, I'm going to end up with 4x plus 3 inside this x function. So I'm replacing this x with this whole piece. Does that make sense? Like this is kind of getting replaced. And then I'm going to solve this, okay? So I know my numerator is going to be 4x plus 3 minus 3. These guys will cancel, right? Whoops. And I'm going to be left with 4x over 4. I know these guys will cancel. And I'm just going to be left with x. Now, if you remember, my original piece is y, right? So when my 2 functions create this y equals x piece, this y equals x answer, when I plug one into the other, I know that they are inverses of each other. Let's say it was, instead of 4, let's say it was 5, right? If I ended up with 4x over 5 at the very end, this would not constitute as an inverse because it's not exactly y equals x line. Okay, so again, you can do it the way that we've been doing up until now, just solving the equations as is, or you could try this new method. I don't think teachers really care. I don't think that there is an issue with doing one way or the other. Some might be a little bit easier than others, depending on the type of equation. Okay, I will see you in the next video, and happy studying.